Good afternoon, everyone, and welcome to RTDology, Burns Engineering's online training series. I'm Jeff Wiggin, National Sales Manager of Burns Engineering, and presenting today will be Bill Berquist, Senior Application Engineer. Today's presentation, Troubleshooting RTDs and Thermocouples, is part of our series of web-based training modules designed to help you better understand temperature and achieve your measurement goals. If you've joined us for any of our previous sessions, we'd like to welcome you back. If this is your first time, welcome. And when you get a chance, do check out our previous presentations on our RTDology channel on YouTube. Simply go to YouTube and search on RTDology, and the recorded sessions will pop up. Before we get started, just a few housekeeping items. To respect everyone's time, we'll make every effort to limit the presentation and Q&A period to 1 hour. We do highly encourage questions, so please type them into the Q&A or the chat box on your screen and send them to host and presenter. We'll attempt to answer as many as time allows. This session is being recorded, and we will provide a link to all participants as soon as it's available, so don't worry if you miss something. If we do not get to your questions or you need some additional assistance, there will be contact information provided at the end of the presentation. And finally, our goal is to answer your temperature measurements, questions, and challenges. So we've put together our RTDology series with an eye to the most commonly asked challenges, issues, and questions. But if you have a particular topic you'd like to have considered, do give us a call and we'll see what we can put together for you. That covers the housekeeping, so without further delay, here is Bill Berquist to provide some background and assistance with troubleshooting RTDs and thermocouples.
All right, well, good morning and good afternoon, everybody. What we're going to talk about today is how we go about determining where the problem is in a temperature measurement loop. And we'll actually look at the construction of RTDs and thermocouples both, so hopefully to help you a little better understand how they can fail and what to do about it if they do fail. I think everybody's kind of been in that situation, especially since you're listening in here, of you've got some mysterious problem happening with the RTD or a thermocouple or your temperature measurement, not quite sure what's going on. Hopefully we'll answer some of those issues for you. And then at the end, we're going to ask for anybody to present their own problem that they have had or are having now, and hopefully we can answer that question and help a few other people that may have a similar failure mode. So first off, we'll talk about the construction of an RTD, resistance temperature detector. There's a couple different styles of sensing elements that are used. This one is what we call a wire wound sensor, and this is a little coil of platinum wire, 7/10,000ths diameter is a pretty common size for the actual sensing wire. It's in a ceramic tube. It's about a 1/16 of an inch diameter and about an inch long. So it's a pretty small device, and you can imagine these wires can be a little bit fragile. The other style is a thin film sensing element. Now these are a lot smaller, 80,000ths in width and a little over 1/8 of an inch long. Lots of different sizes of these around. This one's a pretty common size. And here you can see this little kind of gray stuff here is the actual platinum, which is deposited on a ceramic substrate, and it's put on in a little trace so that they get the right resistance value at 0 degrees C. This blue stuff is a glass material that's put over to hold the external lead wires on, and these are usually platinum, fairly small diameter, about 10,000ths, and some thin films will use a little ribbon instead of a round wire. This is one of the weakest spots on a thin film, right where these leads are attached to the little ceramic piece. And then these things are packaged a couple different ways. One of the more common ways is with a mineral insulated cable. And this is a cross section of that where we see the internal lead wires and this ceramic powder which is compressed around those wires. It does a really good job of making the probe very durable. It makes it also bendable. Another style of probe would be the tube and wire, where we just have wires running inside of a hollow tube, would not have this ceramic powder inside of it. And when we transition from these internal lead wires to the external, that area is potted in epoxy, and it does a fairly good job of sealing the lead wires into the probe. And this is an important part of the probe construction because it needs to keep moisture out of the probe. We're going to talk a little bit later about what moisture can do if it gets inside the probe. It can cause a temperature measurement error. The epoxy does a good job of keeping out water vapor, but if you get liquid on it, a lot of manufacturers use Teflon insulated lead wires, and as we know, the only thing that sticks to Teflon is frying pans, and it just doesn't stick to Teflon insulated lead wires. There's some things you can do to improve it a little bit, but liquid water will make its way past that connection. And then the external leads, typically nickel or silver plated copper, and then Teflon, PVC, or some sort of plastic insulation covering those. So that's kind of what kind of the basics of what's inside of an RTD. On the outside, they generally kind of all look the same, but inside is where the things are a little bit different. So some of the failure modes that I just kind of pulled together some of the more common ones that I hear about. The first one is erratic output, and this is usually caused by some kind of radio frequency or electromagnetic interference. It can also be an indication that the sensor was damaged. You might see where the temperature was running along and all of a sudden it went open circuit or it spiked way up in temperature. That can be an indication of one of those internal lead wires is partially broken, and it might be, as the probe vibrates a little bit, it might be making contact and breaking apart, or just have some portion of breakage. If it's radio frequency or electromagnetic stuff from electric motors or communications radios and things, those things will generally cause kind of a sawtooth spike in the output. Once in a while, I've heard where people have experienced a step change in temperature, where it will, as soon as the motor comes on or radio gets keyed or whatever, the temperature will either jump up or down. And the way to fix this is to use shielded wire. And the connection head on the RTD assembly should be made out of metal, and it can even ground it to help in more serious cases. And then the other way to help this is to route the wiring away from the noise source. So if you have some variable frequency drives on an electric motor, those are really bad. We need to keep all the wiring and things away. We did have a situation recently with a local microbrewery where they had some of this kind of issue with some erratic output and the step change in their temperature measurement. It was in one of their, I don't know, Jeff, if you remember what part of the process that was, if it was the mash tun or if it was one of the other fermenting issues with the brewer.
I think it was in the mash tun.
Okay. So anyway, they had the power cables and the RTD wires all run into the same junction box on the wall, and that's where the interference was coming from. So the fix there was to separate those two and have a separate junction box for the instrumentation and one for the power going to the mixers and the pumps and other things like that. So that turned out to be a fairly easy solution, but took a little bit of time to separate out the wiring. If symptom is just no signal whatsoever, make sure we have the thing wired correctly, or maybe the probe got damaged and it just went open circuit. we had another situation, I recall, with just a step change in output after the probe was put into service. You know, this can be a couple different things. One is just there's a lot of vibration, and it causes the temp sensor, the little sensing element, one of the lead wires to break, or one of the actual sensing wires to break. They're very, like I said before, they're very small, and if it's not all packaged correctly, they can be pretty fragile. One of the more common things is that the probe may have picked up moisture, and when water gets inside the probe, it's going to cause shunting between the element coils, and that's going to cause a drop in resistance and a drop in indicated temperature. And now when you put that probe into service in a hot application, for example, it's going to drive that moisture out, and the indicated temperature is going to jump back up to where it should be. And usually that's an indication that the moisture seal in the probe has been compromised, and it's a good idea just to replace the probe at that time. Another mysterious problem we had recently was it was just in a large storage vessel, and it had a couple different temperature sensors in it, different locations in it, and one of them would just go to 0 and not give any signal, and then it would come back in again and give a good temperature reading. But we did a little bit of troubleshooting, found out, you know, the probe was okay, which, and then eventually, it was connected to a transmitter also. We checked that, checked all the wiring, and all of that stuff was okay. Eventually, the problem was found farther away from the system in another part of the measurement loop. It was another piece of equipment they had in there to help record this measurement, and that's where the issue was, and it was internal to that. It wasn't real obvious at first. It was a new piece of equipment. You wouldn't expect it to go bad, but in this case, that's what had happened. So another one, moving on here, the output changes after a short time in service. And this is another kind of mysterious one where it's usually due to like real high vibration or shock. Water hammer especially can cause an RTD to fail quite quickly. And here, the ways to get away from that would be to relocate the sensor. Had a situation where there was they were pumping a fluid through a pipe, and then they had a steam injection just upstream of the temperature sensor, and when that steam would shoot in to heat up the liquid, it would cause just a little bit of water hammer, and it would, after it did that a few times, the probe would go open circuit or would start drifting up in indicated temperature. Solution there was we just beefed up the RTD and made it about I think we ended up with about an inch diameter, so that it would not shake or be affected as much by that steam injection. And you know, there's a couple of tests that you can do to the probe too, checking the ice point resistance just to verify that it is in fact, you know, the probe that's where the output is changing and it's not someplace else in the temperature measurement loop. And then if the vibration or shock is really bad, about the only other thing you could do would be to replace it by using a thermocouple. They're going to be a lot more resistant to vibration or shock damage. And then we had a little more detail here about how we know what is a correct wiring connection to your chart recorder or a controller. There are some standards for RTD lead wire colors. Not all the manufacturers follow these exactly. They'll have some of their own codes. Part of it is historically, for the last probably 50 or 60 years, the red and white lead wire colors have been kind of the unofficial standard. Now the ASTM and the IEC standards will specify the little bit different colors here. So we have black or gray and a yellow, and then the historical ones for like this dual 4-wire, it's 2 reds and 2 whites, and you may see 2 yellows and 2 blacks or gray colors. I guess we use the red and white. It's just a historical thing with us, and I think Rosemount uses that same coding, and I've seen several others that do the same thing. So you're going to maybe see a little variation there. But the circuit is really fairly simple. We've got the sensing element here with the two red leads connected to one side of it and the whites connected to the other side. And these are for lead wire compensation. And I guess we'll talk a little bit more about that. But the reason for this is that you only want to read the resistance in that little platinum sensing element. You want to exclude all the lead wire resistance. And that's not actually possible in this 2-wire setup. If you do have a 2-wire setup, you have to, if you want to eliminate the lead resistance, you have to measure the resistance in those leads and then somehow subtract it out in your, either in a offset in a transmitter or a controller or some other peripheral connected to that circuit. The other thing I didn't mention here is this, some of the manufacturers use the green color instead of the yellow here too. So you're going to see a little bit of variation there. Again, we're back to our little sensing element diagram here and insulation resistance. And really, when you're checking an RTD probe to see if it's okay, this is the very first test that you want to do. Let's say you've got your temperature shifted and you don't think it's where it should be. I would start with the probe, pull it out, check the insulation resistance, and see where it's at. And that's a real simple test. We hook it to a meg-ohm meter, 50 volts DC, and it should be about at least 100 meg-ohms at room temperature. You really don't start to see a large error until you get down below 1 meg-ohm. The reason the spec is high at room temperature is that the insulation ability of the materials inside the probe degrades as the temperature goes up. So that insulation resistance is going to drop. So we start out with 100 meg-ohms at room temperature, and if you're using that probe at, let's say, 400 degrees C, it might be down to 5 meg-ohms or 10 meg-ohms. And for those of you that like a little math with your insulation resistance, we do have a little equation here where you can calculate what that effect is. Our example here will take an insulation resistance of 0.1 meg-ohms, and that equates to about a 0.26 degrees C lower than actual temperature. So it really needs to get down there before you start to see anything real significant, but it is a pretty important first step when you're checking or actually verifying the function of the probe. The next step to do would be to verify the resistance at the ice point. This is pretty simple to make up a little ice bath with some crushed ice, stuff the probes in there, and measure it with an ohm meter. And if you don't have an ohm meter that does lead wire compensation, you can do it manually by just measuring the resistance in the 2 red leads, and then subtract that from what you measure between the white lead and one of the reds. So we're kind of just doing a manual lead wire compensation, and that works pretty well. So you're going to get, you know, it should be 100 ohms, plus or minus typically 0.06 or 0.12 ohms. And those numbers, the tolerances are governed by the two standards, the IEC and the ASTM standards. This shows it in graphical format, which is, I don't know, probably not too useful. It just, I guess the biggest thing you get out of this is that right at 0 degrees C, that's where the tightest tolerance is, and it's where all the manufacturers adjust the probes right at that point. As you move away from there, the tolerances get bigger. And those tolerances can be calculated by using these equations. So for example, if we have an ASTM probe and it's the grade A, which is it's plus or minus 0.06 ohms at 0 degrees C. And if, let's say we're at 121 degrees C, we plug the numbers in here, and I think we end up with something like a plus or minus 0.33 or 34 degrees C as the interchangeability. And one of the things people ask is like, oh, well, is that the accuracy? Well, it's roughly 85 to 90% of what the accuracy is, because this does not include any long-term stability, self-heating, hysteresis, you know, other little factors that come into play there. But it's a pretty close approximation of what you can expect for accuracy. So a couple more things to look at. We've had issues with people not being able to tune their measurement loop. You know, they'll put some settings in, and then the process will either get too hot or too cold, or you know, something, it just won't be working correctly. And that's usually because the time response of the probe is either too slow or too fast. A couple ways to fix that. You know, usually if the probe is too slow, we need to replace that probe with a different design, one that's going to respond faster to the temperature. And if an RTD isn't fast enough, then actually a thermocouple can be a more accurate device for situations like that. If you have a situation where it responds too fast, if it's a freezer or an incubator where you're putting product in and out of the freezer or incubator, and you don't want an alarm to go off while you're, you know, taking just a couple minutes to switch loads, we can add some kind of thermal insulating material around the probe. I've seen the little bottle of glycol used. There's a Teflon sleeve, kind of like a little Thermowell that you can put around it. There's also the option of making some adjustments to a transmitter, if that's part of your measurement loop, or some controllers and chart recorder, for example, may have a time delay that you can set in. I know of one transmitter in particular, you can set it up to a 60-second delay, so you can open the door and, you know, change out your material and close it back up, and that transmitter is not going to be taking a measurement, you know, for at least 60 seconds. So it's not going to set off an alarm or do anything that you don't want to have happen. Situation where we have a probe that checks out okay in the lab, but they stick it back into service and it reads completely wrong. And almost 100% of the time, this is due to stem conduction. This is one of the bigger problems that I see with temperature measurement with RTDs and thermocouples. There are some fixes to it. Some are easy, some are more difficult. If you can increase the immersion length of the probe, that's the easiest fix. replacing the probe with a different style that might be more tip sensitive, or some other design feature that helps it be less susceptible to stem conduction. That's also a good solution. If you can insulate around the outside portions of the assembly, that's also a really simple, quick solution here. Because what's happening is that if the probe is in a hot process and you've got 70-degree Fahrenheit room temperature, it's going to have a bit of a cooling effect on that probe, and the probe's going to see that if the immersion length isn't sufficient or you don't have the right style probe installed there. So this is just easy to wrap some insulation around it. I've even had people, they'll take off, a sweater or jacket or have a blanket, and they'll just temporarily wrap it around the thing to see if it comes back up to the temperature that they're expecting. And a lot of times just something like that is enough to troubleshoot that as the problem. Just anything to insulate that exterior portions of the probe from the ambient conditions. And we had one situation where it was a bit of a mystery. We checked the probe and, check the process and double check the temperature of the fluid running through the pipe and everything. And finally it boiled down to the fact that there was a fan blowing because there was an operator that was in that area and they had this fan running to kind of move the air around. And that was enough to cause a little bit of a cooling effect on the probe. And just moving the fan so it wasn't blowing on the probe was a real simple fix there. Difficult to figure out, but it was sure a very simple fix. The last thing on the solution list there would be to make sure that the temperature probe is sized correctly for a Thermowell in those situations where there is a Thermowell. And then if the probe diameter and the bore diameter are not matched up closely, that can also cause a bit of a temperature measurement error. Now, the graph here shows an expected measurement error versus the immersion length. And now this is a 1/4 inch diameter probe installed in a Thermowell, and there's 100 degrees C difference between the process temperature and the ambient conditions. And we can see here where we need to get out to probably at least 4 inches of immersion before we have less than 1/10 of a degree C stem conduction error. And by the time we get out to about 6 inches, it's pretty much gone. And all these numbers here are highly dependent on the properties of the fluid that you're measuring, the flow rate, and if you use a heat transfer paste inside the well and everything. I mean, there's a lot of factors that go into this. So these are, I guess, what I would call some pretty rough guidelines. I'd look at this, and if you want to use a 2-inch immersion Thermowell, you probably aren't going to get real good results. So you'd have to, maybe think about ways to bump that up a little bit. And if we go down to a 1/4 inch diameter direct immersion sensor, we can see that we get just over 3 inches here to be less than 1/10 of a degree C stem conduction error. And then finally, we can make further improvements by going to a smaller diameter probe, something with a very short sensitive length. And here we're down to about 2 inches for that same stem conduction error. So with that, some other sources of trouble I've run across, corroded terminals where 3-wire circuits and for RTDs are really susceptible to this. All 3 of those leads going down to the sensing element have to be exactly the same resistance for the lead resistance to work correctly. If they're not, you're going to get a bad reading. A 4-wire circuit has the advantage of compensating for all that kind of stuff, and so it does make up for some poor maintenance. Here we just have a few examples here where if you use a terminal block, it should be something that doesn't soak up moisture, because you can get that insulation resistance problem right at the terminal block. Lead should be tinned in really good shape, or spade lugs. If you use a connector, really high quality, preferably water resistant, watertight, gold plated contacts. And if they are mated and unmated frequently, probably a good idea to either use a 4-wire circuit or change out the connector on a regular basis if it's a 3-wire circuit. Here, if you have a lead where part of the strands are missing in a 3-wire circuit, you hook up to right here, you're going to have higher resistance in that lead than you are in this mess here or this one, and it's going to cause a measurement error. This connection head down here, this was kind of a special situation where we had the right terminal block, but there was some flexible conduit running away from this thing, which was not airtight, and it was a real dusty area. And this dust was electrically conductive. It got inside the head all over the terminal block, and it caused some shunting between the wires there and a bad temperature reading. So with that, I think if we have any questions now, Jeff, we could probably go through some of those.
Yeah. Thanks, Bill. And yeah, just a reminder, if you do have any questions, go ahead and type them into the chat section or the Q&A section on your screen, and we'll go ahead and answer those questions. If you've run into, and before Bill goes through thermocouples here, if you are experiencing some kind of anomaly now that you want some help in troubleshooting, you can go ahead and type that. We'll have some time at the end of the session to go ahead and try to get an answer, or at least find some possibilities as to what might be going on. So give that some thought, but do it at any point. Go ahead and put your questions in. So I think it looks like there's a couple people typing right now. So Bill, if you just want to go ahead and continue.
Okay. Well, we'll just keep moving on here right now. Certainly, I put a lot of stuff in here, and I'm kind of going a little bit fast. I hope if everybody can keep up. So if you do have some stuff where I went over it too quickly, feel free to interrupt us and ask. So thermocouple construction. Some of this is very similar to RTD construction. In fact, I use the same photo here because they look the same. Right here with the mineral insulated cable, these lead wires would be welded together to form the thermocouple junction, which is a good example of it right down here. So this, in fact, would be a dual thermocouple. So they'd have these two welded together and these two. The same epoxy seal is used. It could be a ceramic seal if it's used in a higher temperature application. And the same material for the lead wires. Another style of thermocouple construction is tube and wire, which is exactly what it says. It's just a tube with some thermocouple wires run down inside of it. And this other type on the bottom here is just a couple thermocouple wires with some ceramic insulators around it. Sometimes these are used as an exposed junction, where this hot junction will be exposed right to the process. Sometimes these are installed into a Thermowell, or even just a small tube, either a metal or ceramic tube. And then there's the ungrounded or grounded junctions. This would be typical of the mineral insulated cable style probes. where that hot junction is welded right into the probe sheath for the grounded detail, and then the ungrounded where it's isolated from the probe sheath. This is probably the most common style. It's if you have any electrical noise around, this helps to minimize it by isolating that thermocouple wires from the probe sheath, which may be exposed to, stray voltage or static electricity or other types of interference like that. Your instrumentation needs to be set to accept whichever type, grounded or ungrounded, that you might have. And some of the issues that I see with thermocouples, number one is erratic output, and again, radio frequency and electromagnetic interference. Thermocouples are much more susceptible to this than an RTD, so it's a good idea to always use a shielded cable, and if you can add a transmitter right at the location of the temperature measurement, and then you're running a 4 to 20 milliamp signal, that's a good solution also. Is that the 4 to 20 is much more resistant to any kind of interference. With a thermocouple, it generates a millivolt, and anytime you're trying to measure something that small, it's going to be difficult to do and easily interfered with. Now, thermocouples do drift quite quickly. Usually the higher the temperature that they're used at, the faster they're going to drift. And the fix for that is just to replace it. They're usually not very expensive, and it's really just the best way to do it. If you're seeing a short life from a thermocouple, that's usually due to corrosion or contamination of the conductors, and this could be it's just the wrong type thermocouple to use. The Thermowell could be the wrong style to use. It might be you're using a metal Thermowell where it should be a ceramic Thermowell for high temperature applications, for example. And then if you're not getting any kind of a signal out of your measurement loop, you could start first with to check to make sure that hot junction isn't broken by just doing a simple continuity check between the two lead wires. You could have the wires connected incorrectly at the controller or your chart recorder. And there, you need to check the polarity of those wires. And the way to do that, there are color codes that go along with these. Like we'll have the type E as a purple and red. And if you were to look at these wires, I mean, right now on the screen here, they kind of look like they're both kind of brown, but there's a purple stripe on one of those. So you'd know that that is the positive. The red lead is always going to be the negative. On a type R, this can be a little more difficult to see. This manufacturer has it labeled R with a plus, and I assume the plus is this lead here, but it's a little bit, it might be a little bit difficult to see this and figure it out. The type T, they're blue and red. Here you can see that this one's obviously a blue lead, so it's going to be the plus. Type K, another real popular type, is yellow and red. Type J, those are red and white. Some of the short life on a thermocouple can actually be caused by some internal corrosion that can happen. We have an example here of what's called green rot. So this happens to be in a type K thermocouple, and you can see all this corrosion that formed around the lead wires, and it actually decreased the cross-sectional area of that wire just because it's been eating away at it. And this was probably used at a real high temperature, and there wasn't enough oxygen present to prevent this. And you'll also notice that one of the wires will become magnetic. Most of the leads in type Ks are not really magnetic, but if you know it's a type K and you suspect that this might be happening, a little test with a magnet will help determine what's going on. Or you can do like we did, just cut the tip off the probe and look at the wires. Some other ways to check your thermocouple would just be to use a thermocouple simulator. You just hook this into your measurement loop and input a temperature and see if your control system is giving the same thing, and put the thermocouple back in and see if you're getting the same numbers. So just another way to quickly check. Extension wires, these need to be the same type as the thermocouple. If it's mismatched, you're going to have a bad measurement. Another possible issue too in your extension wires, if you have any kind of, if it's running through some moisture or it shorts together any place, it's going to cause another measurement junction. And so you're going to be measuring somewhere along your lead wire run rather than at that hot junction down in your process. That one can be sometimes kind of difficult to find. If you use kind of the plastic insulation on the conductors, that's usually not an issue. I have seen where if it's fiberglass insulation, stuff can get in there and actually short them out, and the insulation still looks okay, but it's kind of porous, and so moisture or conductive dust and stuff can cause an issue.
Hey, Bill, we've got a question. As long as you're talking about thermocouples and extension wire there's a question as to if there are any guidelines on the length of the hot junction based upon the diameter of the lead wires. In other words, I think he's asking, is there any type of limit on the length of the thermocouple based upon the diameter of the wire?
Oh, not that I know of. It's usually, the little ball that's formed on the end is roughly, because you're just melting back those lead wires, it ends up being about the same, 2 diameters of the wires in size. But I'm not aware of any specific guideline there. I guess if anybody else listening in is, sure, let us know. I'm not aware of any.
Right. Or if we've misinterpreted your question, by all means, go ahead and restate it, and we'll try to get you an answer.
So one of the other, this RFI EMI stuff, using like I mentioned, a shielded cable, and it should be left open at the probe end. Don't ground it to the probe or anything at that end. It should be grounded, or the shield wire should be grounded back at the instrument end, so that it's taking all that whatever electrical interference and it's taking it back away from the probe and draining it off to an earth ground or the whatever grounding system you have. It should be just grounded at the one end. If you hook it to both ends, it really doesn't work all that well. So, and keep the extension wire as short as possible. And I'd already mentioned adding a transmitter into that loop. So, but this is by far one of the biggest issues I see with thermocouples is this RFI EMI stuff. And kind of repeating myself a little bit, but just a little more detail here, just to make sure that that thermocouple or RTD, it applies to both of these, closely matches the bore diameter of the Thermowell, and that the probe is bottomed out firmly in that Thermowell. We should have about a 10/1000 or tighter fit between the probe and the well. If it's bigger than that, you will see some measurement error because you're not getting as good of a thermal contact between the two, and there's an air gap, and it can that air tends to cause a bit of a stem conduction effect because it's going to be circulating in and out of that well up into the connection head. And if you got a hot process and 70 degree F ambient, it's going to have a little bit of a cooling effect on it. But you tighten up that fit up, and then part of that's going to go away. You can also put a heat transfer paste in, and that's really going to displace the air that's in there and give you a much better temperature reading. So finally, we're getting to the end here, and I just wanted to see if anybody had any kind of a failure mode or a symptom that they're seeing that we could talk about right now. If you could plug that into the search or the chat or the Q&A, we could sure talk about it right now.
Okay. Again, if there are any questions, whether it's a failure, a symptom, or any other questions that you have, go ahead and type them in, and we've got looks like we've got a few minutes here for questions, so we'd be happy to get those answered. On a previous question, it does look like there's we talked about the hot junction. A clarification there is really where is the Seabold effect taking place, I guess, is the question.
Well, the way the thermocouple works, and it can actually get quite complicated. If you crack open any thermocouple book, there's going to be a whole bunch of equations and things, and looking at all the different reasons for why this thing generates a voltage when you have a hot junction and the lead wires going from a hot to a cold. If the whole thing is at one temperature, you're not going to get anything out of it. It has to have, the hot junction needs to be, it has to be some kind of temperature differential between that hot junction and where you're measuring it at the other end. And you would typically have some kind of a reference temperature, and a lot of times you can use the ice point. A lot of the instrumentation uses some kind of an electronic trickery to say, okay, this is the cold junction here, so that it can so that you have that differential between the hot and the cold junction, so you get that voltage generated that you can measure. So I don't know if that completely answers the question.
I think, Bill, if you look at the last question there, that probably
a little more detail here. So, okay, so the hot junction was 2 feet long. The probe was inserted into a hot environment. Would it be measuring the terminal end or the closest junction to the meter? It'd be the closest junction to the meter, like I said earlier, if you were to have another accidental junction outside of your process, it's going to be measuring it there. So whatever's closest is the way that's going to work. And I believe that's the right answer for that. So.
Okay, and then a question about a stirred bath, and I may need a little bit more information on this. I'm not sure how much is enough and how close is too close or too far. I'm not sure what that's in relation to, but maybe you do.
Well, okay, I think it's probably with the ice bath. And if you're just doing a quick check to see if like an RTD probe is working correctly, if you're checking the ice point resistance, the best way is to use crushed ice that's been made from distilled water, so it doesn't have any contaminants in it that can change its freezing point. And you really don't have to have it stirred. If you want to really get the best accuracy out of it, sure, yeah, you need to have it stirred, but filling an insulated container with crushed ice and then pouring in just enough water to fill in the gaps in between the little pieces of ice. You don't want the ice to float. You just need to put in enough just to fill those in. And then wait, 5-10 minutes or so for it to kind of all stabilize with the probes in place, and then measure. If you do, I think if you get into like all the nitty-gritty details of making the perfect ice bath, you got to wait longer, and it should be stirred, and some other things, and then you can get out to that third and fourth decimal place. But if we're just checking a RTD to see if it's within that plus or minus 0.06 or 0.12 resistance window, don't have to get too fancy. So, and then the probe should be fully immersed. If you've got a really long probe, you need, probably 4 or 5 inches of immersion would be sufficient. So,
okay.
I hope that's the right answer. If I interpreted that. If not, let me know.
Yeah. We've got another couple more questions here. Another question: what would cause a thermocouple to read correctly at 250 F, then suddenly step down to incorrect reading by 50 degrees F, then 24 hours later jump back to the correct reading in another step change?
Wow. Yeah, I've actually, I've heard of something similar to this. And, I guess I would suspect that there's some machinery or something that's starting up in the facility and it's on a regular schedule, and then it's causing it to change like that. There are so many things that can come into play here. Even like a bad grounding system in the building. If it's a really old building, I've seen where there are more grounding issues within that, where they'll have some stray voltage actually is getting into their grounding system, and that can cause a thermocouple to read poorly, to jump up and down like that. It could be something as simple as, someone's turning on a light switch somewhere and that shoots power into that grounding. And probably the first thing I'd try here would be to somehow better isolate the thermocouple and the readout equipment from the rest of the electrical system within the building. Because it's got to be, it's typically not the thermocouple when you see something like this. It's someplace away from it in the electronics that it's connected to, or the facility electrical system.
And Bill, when you say it's in a situation like this, it's not typically the thermocouple, why would that be? Or can you say a little bit more about what you would see if it was a thermocouple issue?
Well, if it were the thermocouple, it would change, and it wouldn't change back. There's really no way I can see where it would change its, its voltage back and forth like that. And it sounds like this is a pretty regular occurrence. If it were just once, I might say, well, maybe a lead wire is starting to break or something, but that's pretty rare in a thermocouple. And this just seems like it's something to do with some kind of stray voltage or RFI EMI type stuff.
Okay. And then we've got a similar, I guess somewhat of a similar question. They've got an RTD that seems to work fine when it's at temperature, about 150 degrees C. But then once they shut down the process, and then the next time they start up, it doesn't seem to be tracking until it's been up to temperature 150 degrees again for some amount of time, and then it seems to stabilize.
Yeah, the first thing that comes to mind is that it's an insulation resistance thing. If the change isn't very large, I would suspect that. The other thing I've seen is I've seen some potting material get damaged by being over-temped, and that can cause a time response change in the probe. Well, that's usually a permanent thing, though, where the probe is working good initially, and then later on they've had trouble tuning that measurement loop, and it's because the time response of the probe slowed down because the probe got over-temped, and the potting material properties changed because of that, and it acts more as a thermal insulator than a conductor.
Okay. If again, if anybody does have any questions or has any symptoms that they'd like to have us take a look at, go ahead and type them into the Q&A or the chat box, and we'll try to get those addressed. Got one more here right now. I think I might have an RTD with an incorrect alpha. How would I go about checking that?
Well, the easiest way to do that would be to check it in an ice bath to make sure that it's, 100 ohms, plus or minus 0.12 ohms. Just make sure that that's pretty close. And then if you can test it at 100 degrees C, the resistance that you get there will closely match what the temperature coefficient should be. So for example, if it's supposed to be a 0.00385 coefficient, at 100 degrees C, that probe should read 138.5 ohms. And if it's some of the other coefficients would be like the 0.003902, and that one's going to read 139.02 ohms at 100 degrees C. It's not going to be, that's probably plus or minus, a few hundredths of an ohm roughly, but it should be close to that. That's a real quick, easy way to test that.
Okay. So it doesn't look like we have any other questions at this point, but if somebody does have a question in the future, by all means, go ahead and shoot us an email or give us a call. We'd be more than happy to help you try to figure out what's going on, whether it's one of our sensors or somebody else's sensors, doesn't matter. Go ahead and give us a call, and we will try to get you an answer so that you can get your problem fixed. Also wanted to remind you, we do have our next RTDology event is September 14th on selection and application. We would love to have you visit us. You can visit our YouTube channel, RTDology, for full-length presentations as well as short clips on different topics. And we will be sending you a link to a recording of this particular session. We aren't necessarily sending the slide deck, but if you have a specific request for that, we can do that. But we will have a recording posted up on YouTube, and we will send out a link for that probably within the next couple days. So unless there are any other questions, Bill, any final comments?
I guess, the easiest way to find that on YouTube is just to go to YouTube and go in the search box and just plug in RTDology, and it'll take you to the whole series of presentations we've done. And there's also some kind of shorter clips that are like 5 or 10 minutes on how to make up an ice bath, for example, how to do an insulation resistance test, and a few others. So that's I guess that's about it then.
Okay, with that, thank you all very much for attending. We hope to see you next time, and have a great afternoon.